Hi, this video is to talk about additional topics of counting and probability for our statistics course. You should watch this video after you've watched the introductory counting and probability video that was posted last week. In this video, I'm going to discuss some definitions related to events being disjoint, and then we'll talk about the addition rule of probabilities. We already saw the multiplication rule, some additional probabilities, some more introductory topics. Here we'll learn the last probability rule of addition, and then we'll look into some counting techniques using permutations and combinations. So our first definition is the words mutually exclusive, also known as disjoint. So two events are mutually exclusive when they cannot both occur at the same time. In a Venn diagram setting, we see on the left two events that are mutually exclusive. There's no overlap, so there's no area where you could both be in event A and event B at the same time. On the right, we see two events that are not disjoint. They are not mutually exclusive because there is this overlapping portion where you could have both events A and B happening at the same time. It's important we understand the definition of mutually exclusive because there's two versions of our addition rule. One version will be the general version, which will work in either situation, whether it's mutually exclusive or not. But if we have mutually exclusive events, events that cannot occur at the same time, there's a simplified version of the addition rule for that sort of event. So one thing we need to talk about before getting into the addition rule is how to tell if two events are mutually exclusive or not. So I've put an example here where two examples really. So the first example is you're rolling a die and you have an event A where you're rolling a 3 on the die and an event B where you roll a 4 on the die. If I were to draw the sample space, these are normal 6-sided dies, we would have our event of rolling a 3, our event of rolling a 4, and then all the other possibilities for our roll would exist elsewhere in the sample space. The event of rolling a 3 and rolling a 4 are mutually exclusive. There's no way you could roll the dice once and get both a 3 and a 4 at the same time. So these would be disjoint or mutually exclusive events. Now when we look at the second example, we have choosing a random student, and we're randomly choosing a male student as event A, and randomly choosing a nursing student as event B. So if we think of the sample space as being the set of all students, we have somewhere in this space the set of male students. There's also all the female students. And then there's the set of nursing students. And there is a possibility we could have a man or a male student who is also a nurse. So we do see this overlapping area. So these are not mutually exclusive events because you could randomly choose a student who happens to be a male student and also happens to be a nursing student. Not disjoint, not mutually exclusive. With this definition of disjoint or mutually exclusive events in mind, we have the addition rule, which is different than the multiplication rule. So looking here, we use the addition rule when we're looking to find the probability that one or the other event will occur. With the multiplication rule from last time, we looked at both events happening. We had and in between event A and B happening. Here, with the addition rule, we're looking at one or the other. It's also allowable for both events to happen. But when we apply the addition rule to find the probability that event A or event B occurs, we find the probability of event A and the probability of event B and add those together, but we need to subtract any double counted occurrences. Any time where both event A and B occurred, it's being counted in both the probability of A and the probability of B, when really it refers to only one outcome. So we have to subtract that overlap, the probability that both events are occurring. If the events overlap, if they're not mutually exclusive, there is some overlap, and so we need that subtraction. It's necessary. If we have events that are totally disjoint, then there's no overlap. Then we have event A and we have event B, and they are totally separate. So we would be subtracting 0, because the probability of having both happen, there's 0 outcomes possible. So we'll look into an example using this, actually 2 examples. One where we have mutually exclusive events, and one where we have an overlap. So the first example, you are selecting a card from a standard deck of 52 playing cards. And we're asked to find the probability that the card is a 4 or an ace. Slight typo there, my mistake. I should say an ace. So you have a deck of cards, you pull a random card out. What's the probability you choose either a 4 or an ace? It's impossible to choose one card and have it be both a 4 and an ace at the same time. So that is why we have mutually exclusive events here. So the probability that we find a 4 or an ace, according to our general addition rule, that would be the probability of choosing a 4 plus the probability of choosing an ace. And we would subtract any overlap, but because these are mutually exclusive events, I don't actually have anything to subtract. So the probability of choosing a 4, I can find that just by computing the ratio. There's 4 cards that are a 4 clubs, spades, hearts, and diamonds, out of the 52 cards. And then for an ace, there's 4 aces as well. So 4 out of the 52 cards, which gives us an overall probability of 8 over 52. And that can be simplified by dividing by 4 on each as 2/13. And if we're using a decimal approximation, we'd call that 0.154. So our probability of choosing either a 4 or an ace is roughly 0.154. The second example of the addition rule I've provided here has an overlapping section. So you're rolling a die, a 6-sided die in this example. Find the probability that you roll a number that is less than 3, or you roll an odd number. So the value 1 is both less than 3 and odd. So that's why we see 1 occurring in the overlap. Other than the value 1, 2 is also less than 3. And other than the value 1, we have the numbers 3 and 5 that are odd. So when I'm looking to find the probability here, that's the probability of less than 3 or the probability of rolling an odd. These are not mutually exclusive. So my addition rule would look like a probability of rolling less than 3 plus the probability of getting an odd roll minus the probability of getting an odd and less than 3. So the probability of rolling something less than 3, there's 2 ways. We could get a 1 or a 2 out of 6 possible outcomes. The probability of rolling an odd, there are 3 odd outcomes out of 6 total. And then we're going to subtract the probability that we roll a 1, a number that is both odd and less than 3. In performing the addition and subtraction here, we have 2 plus 3 is 5, minus 1 is 4. We get 4/6, which simplifies as 2/3. Or in a decimal approximation, that's 0.667. So there's our probability. One more example using the addition rule. Here, the information is from a 2-way table. So we have a blood bank that catalogs the blood type, including whether it is Rh positive or Rh negative. So they catalog that you have A negative or A positive or whatever as seen in the table. The information, we're asked to find the probability that a donor that is randomly selected has type B blood or is Rh negative. So are those mutually exclusive events? The answer is no, because you could be both B and negative by having type B negative blood. So there are 8 people who have both B and negative blood. So we need to take into account those 8 people are getting double counted, both counted as having type B blood and getting counted as having Rh negative blood. So when I look to find the probability here, I'm going to use the probability that we choose someone who is B when we're randomly selecting, plus the probability that we choose someone who has negative Rh negative blood, minus the probability we choose someone who has B negative blood, who has both B and negative blood. So using the values in the table, there are 45 total people who have type B blood. So that's 45 out of the 409 people that were in this sample, so over 409. Plus, how many had negative Rh factor was 65. So 65 over 409. And then we subtract the 8 people who have been double counted, both having B and negative blood. So that's 8 over 409 total people. Performing the additions and subtractions, we get 102 over 409. And in a decimal approximation, that is 0.249. So close to a 25% chance of choosing someone randomly who has either negative blood or type B blood. And that is the last example I'm going to provide here in the video for the addition rule. There is a table found in your book on page 161, which summarizes all the different probability rules that we have been discussing. So our classical probability calculation, the empirical probability calculation, right, determining whether the events have equally likely outcomes, or is there a difference between the outcomes probability. If they're equally likely, we use the theoretical or classical probability. If instead we do not have equally likely outcomes, but we have some sort of an estimate from experiments, then we use the empirical approach. We use the empirical probability. We also know how to find the complement of an event, the probability of a complement, the multiplication rule, again, from earlier in the chapter, and then this addition rule that we just discussed. So those are our major probability topics for the course. We're going to continue to use those as we move forward into the next chapters, looking at things related to distributions of our variables, our probability distributions. Now, this video was about counting and probability. So that was the probability discussion. The rest of this video will focus on the counting. Because one thing we noticed, perhaps, from probability calculations is that we need to know how many ways an event can happen. In other words, we need to know the total number of outcomes possible. In many situations we've looked at, that value was given to us, or it was something we were able to calculate and determine very easily. However, that's not always the case. So when we need to look at how to find the total number of events, we need some counting techniques. So we're going to look into permutations, both for distinct objects, meaning when the items or people or objects are all different from each other. And we'll look at permutations for non-distinct objects. Something where, you're trying to arrange, 7 blue flags and 8 black flags and 3 white flags into a nice pattern. And how many ways could you arrange them? Well, the 7 flags that are all one color, all are identical. They're not distinct. So when we have non-distinct objects, we have a slightly different approach. And then after that, we'll look at combinations of events. Combinations are used when the order we put things in, the order we choose, does not matter. And then I'll summarize the counting a little bit with one of our tables from the book. So a couple of definitions so that we can talk about permutations. There's an operation in math known as a factorial. You may have seen it before. It's written with this exclamation point. We perform the factorial of a non-negative integer. So this works for numbers 0, 1, 2, 3, 4, 5, 6, 7, 8. Any number like that could be our value of n. So when we have n factorial, we simply multiply the number n times the integer that came right before it, times the integer before that, times the integer before that, until eventually we get down to multiplying 3 times 2 times 1. And then we have multiplied our entire factorial. The reason we're learning what a factorial is because the formulas, the equations for permutations and combinations use this operation, factorial. So we won't always actually multiply everything out in a factorial because we're going to have these factorials in a fraction. So before multiplying, we'll look to cancel some things so that we can simplify it a little bit so that there's a little less for us to multiply. So for instance, before going into any permutation examples, if we had like 6 factorial, that would be 6, the number itself, times 5, times 4, times 3, times 2, times 1. And when I get to 1, I stop. So I'm just counting down and multiplying all of these items together. If I multiply 6 times 5, times 4, times 3, times 2, times 1, we get 720. So 6 factorial, just an operation that represented the number 720. Okay? So we'll now use this operation in a formula, actually 2 formulas. So we have the permutation, not a combination. A permutation has order to it. It's an ordered arrangement of objects. The number of different permutations of n distinct objects is n factorial. So already we already see that factorial coming into play. Here is our formula when we have n objects total and you are asked to pick from the n objects just r. So perhaps you have 10 friends and you only have 3 concert tickets. How many ways can you pick 3 of your 10 friends to take to the concert with you? That's the kind of question a permutation can answer. And the formula represented here involves using factorials. So in this formula, our notation is going to be, so if I have 10 friends and only 3 concert tickets to share with them, how many ways can I choose? 10 is the total number of people, and we're choosing R, we're choosing 3. So instead of NPR, we see 10P3. That can be calculated using n factorial, where again, n was 10 and r is 3. So we'd have 10 factorial over 10 minus 3 factorial. Now, if I actually write out all the multiplications that those factorials represent, the numerator says 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And in the denominator, I would subtract these first because parentheses is before you would multiply, right? Factorial is like multiplication. So 10 minus 3 is 7. So in the denominator, we just have 7 times 6 times 5 times 4 times 3 times 2 times 1. Before I actually multiply, when we have a fraction, and in the top and bottom there are factors, things being multiplied, and we have identical factors, we can simplify by canceling those. They each become essentially a multiplication by 1. So the 7, 6, 5, 4, 3, 2, 1 in both the top and bottom of the fraction can cancel with each other. And we're left just with 10 times 9 times 8. And 10 times 9 times 8, that's 72 times 10. We get 720 ways you could choose 3 of your friends from your group of 10 friends to take to the concert with you. So this is the sort of way we'll look into computing permutations. There's an assumption with my example that the order you chose the friends mattered, that you would perhaps get a different seat depending on if you were the first friend chosen versus the second friend chosen, sort of thing. That way our permutation is a good formula to choose. So we want to use these permutations when you're choosing objects and putting them in an order, or when the order that you make the choice matters. I do have a few prepared examples here as well. So for instance, say we're trying to find a new 4-digit code. So perhaps this is to unlock your laptop with a quick pin or something like that. So you're trying to find the number of ways that you could make this 4-digit code where you would have no digit repeat at all. So that is from all the digits. When we think of the digits, that is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, sorry, no 10. That would be 2 digits long. So 0 through 9, which is 10 options. So there's 10 choices for digits. And we're trying to pick 4. And the order matters because if my code is 1, 2, 3, 4, and you type in 4, 3, 2, 1, you're not going to unlock my computer. We also have this restriction that we're not allowed to repeat the digits. So there's no replacement here as well. So we're going to see, once a number is chosen, we're not allowed to choose it again, meaning the objects are distinct. The numbers we pick are all different from each other. A code that said 1224 would not be allowed because then we'd have a repeat digit of the number 2. So here we have 10 total values. That's going to be our n, and r is going to be the 4 that we're picking. So we'll see 10p4, which is 10 factorial over 10 minus 4 factorial. Now that denominator, 10 minus 4, that's 6. So we really see 6 factorial in the denominator. And in the numerator, I'm going to start to write the 10 factorial as 10 times 9 times 8 times 7. And then instead of writing 6 times 5 times 4 times 3 times 2 times 1, I'm going to save my time and just write that as 6 factorial because the 6 factorial in the denominator will cancel with the 6 factorial in the numerator. And then by multiplying what still remains in the numerator, we get 10 times 9 times 8 times 7, which is 5,040. So there are 5,040 different codes that you could pick when you are choosing a 4-digit code with no repeating digits. All right, moving on to situations where the objects are not distinct. So that would be allowing your digits to repeat in your code, allowing for your code to have the same number repeated so that they're not all distinct numbers. So when we have non-distinct objects, when we have repeats allowed, we look to discuss this using distinguishable permutations. Because if the numbers you choose are 1, 2, 2, and 4, 1, 2, 2, and 4, I could swap these 2's around in the middle of my code and it would not look different at all. It's indistinguishable. So we will actually not be interested in identifying those as 2 different codes. Instead, we would want to talk about them as being the same code. So that's where we start discussing how many distinguishable permutations are there. When we look for distinguishable permutations, so when we have a situation where some of the objects are identical to other objects, we find the permutations, the number of permutations, using this formula, where we take the total number of objects, n, factorial in the numerator, and then in the denominator, we are multiplying times the factorial of each of the types of objects. I think it's a little bit easier to see the formula and understand it with an example. So let me pull up our example of Jim, who wants to plant oak trees. So Jim wants to plant some trees. He has 6 oak trees, 9 maple trees, and 5 poplar trees. So that's a total of 6 plus 9 plus 5 is 20 trees total. So we see n will be 20. There are 3 types of trees, and in the formula, those were being represented as little subscripts. So we have 3 types, so I'm going to see N1, N2, and N3, where those are the 6 oak trees, the 9 maple trees, and the 5 poplar trees. By my distinguishable permutations or distinguishable arrangements of the trees, I can find n factorial over n1 factorial times n2 factorial times n3 factorial. And that's going to show me how many different ways the trees could be planted in different arrangements. So using the actual numbers from the problem, that's 20 factorial over 9 factorial times 6 factorial times 5 factorial. There's definitely going to be some cancellations that can happen here. So with the 20 factorial, I'm going to write that here in the margin as 20 times 19 times 18 times 17 times 16 times 15 times 14 times 13 times 12 times 11 times 10, and then I'm just going to call it 9 factorial after that point. And in the denominator, that 9 factorial is going to cancel with the 9 factorial. Then I have a 6 factorial, so that's 6 times 5 times 4 times 3 times 2 times 1, also times 5 factorial, 5 times 4 times 3 times 2 times 1. So looking to cancel some things, right? We have the 9 factorial can cancel with the 9 factorial. I can cancel 10 if I use 5 and 2. So I'll cancel that 10 by canceling both 5 and 2 in the denominator, because 5 times 2 is 10. 12, we could use 6 and 2, or we could say 3 times 4. I'm going to go with the 3 times 4. So 12 in the numerator with the 3, one of the 3's and one of the 4's in the denominator. The times 1's aren't really helping us change the value of the denominator either. My goal is to get everything in the denominator to cancel, so I can talk about how many ways there are. So looking at the numbers that are still here, I can cancel the 20 in the numerator by using 5 times 4 in the denominator. And then I see 6, 3, and 2 are still here, so 6 times 3 is 18, so I'll cancel the 6 and 3 in the denominator with the 18 in the numerator. And then I've got this value of 2 still in my denominator. I can cancel the 2 with any of the even numbers that are still in the numerator. So I could cancel it with the 16 or with the 14, but it won't completely cancel those values. I'll use 16 here. So when I cancel 2 in the denominator, I'm dividing 16 by 2, so it's still an 8. In all the other situations, everything I canceled, I was canceling the entire value, so it just became a bunch of 1's being multiplied. Right, so 20 became a 1, 18 became a 1, 12 became a 1, 10 became a 1. Everything is multiplied by 1 when it cancels out. So what's left here? So we have in the numerator some values, but the denominator's 1. It's all been canceled. So there's no fraction left. And in the numerator, just to make it clear, because there's a lot of crossed out, we still have 19 times 17. The 16 became an 8, so times 8, times 15, times 14, times 13, times 11. Everything else in the numerator has canceled. And if we multiply these values together, we're going to see 19 times 17 times 8 times 15 times 14 times 13 times 11. And that is, let me get the number written here. It's kind of big. So we have 77,597,520 ways or arrangements possible. So there's a lot of ways he could arrange these trees and plant them. So that is an example for distinguishable permutations. So these are still things where the order you put them in matters. The difference here being that the items were not different. The 6 oak trees, I could not tell the 6 of them apart. They were just oak trees. If they were distinguishable, if we had 20 trees and they were all different from each other, we would use the regular permutation formula that we saw earlier. One more concept about counting, and then we'll be wrapping up the video here. So the last concept is about combinations. Combinations differ from permutations not only because their formula is different, but because we don't care about the order the objects are chosen. So it's without regard to order. You're still having n objects total, and you're choosing r from those objects, but you do not have any care. There's no difference in the order when things are chosen. So we see the formula here still has factorials involved. There's just one new item. If you're in my current semester of statistics, you have a typo in your textbook for this formula. Please make a note for yourself that the textbook has a typo. In the book, it says that this is n minus 1 in parentheses, which is incorrect. It is n minus r. So we'll look at some example where we would use a combination, and then we'll look at an example to finish off that gives us a combination of counting and probability. being used. So here's our combination example. So we have a manager from the accounting department, and they want to form a 3-person committee, and there's 20 employees in total in the department. How many different ways can the committee be formed? So that is N is the total number of employees to choose from, 20, and we are trying to choose R, 3 of them. So my NCR would look like 20C3, and it's equal to a fraction where the numerator is n factorial, so we'll have 20 factorial in the numerator, and in the denominator we see 20 minus 3 factorial, and then r factorial, so 3 factorial. Writing a little bit of these factorials out, 20 times 18, 20 times 19 times 18, times 17, and I'm just going to go with 17 factorial because in my denominator, that first factorial, 20 minus 3, is 17 factorial. I'm going to allow those to cancel with each other, so I won't bother writing it all out. But there is another piece of the denominator, not just the 17 factorial, also this 3 factorial, which would be 3 times 2 times 1. So making my cancellations, the 17 factorial can cancel. 3 times 2 is 6. I can cancel 6 in part with the 18. So I'm going to do that. That's 6. 18 is 6 times 3. And then the times 1 in the denominator is fine. That means we have a whole number, which is our goal. We should be counting the number of ways, should always be a whole number. So then we multiply the 20 times 19 times 3, and everything else in the numerator has canceled. There are 1,140 ways to choose who will be the 3 employees on the committee. So fairly straightforward, but without practice, this, especially if factorials and combinations and permutations are new, you may feel like you need some work done with these cancellations and formulas. I recommend, working on as many problems as you can in the coming week. That way, when we do meet again in person, we can talk about any of the questions you have from this chapter before moving on to the new material. All right, one last example, and then just summarizing our counting techniques. So in this last example, we have a jury, and that jury is made up of 5 men and 7 women, and 3 members are going to be selected for an interview. We're not asked to find how many ways we could select 3 members. Instead, we're asked to find the probability that all 3 of them are men. So first thing I would like to say is we have to count here. We need to count up the total number of ways. We need to know, would we be using a combination or a permutation? And the way to find out is to think about if the order people are chosen for an interview matters. If you are first, second, or third to be chosen for an interview, the order does not matter. So we're going to use combinations since that order does not matter. And out of the members of the jury, we are looking to select all 3 of them as men. So there were 5 men total. We can select 3 of them. So we will see 5C3, the combination of the 5 men, choosing 3 of them. There's different ways you could choose which 3 of the 5 men, and that's what that will represent. But that is not only what we need here. We also need to choose none of the women. So of the 7 women, we want to choose 0 of them. And once we know that value, we then want to divide by the total number of ways to choose the committee, regardless. So this multiplication that we have here is using the fundamental counting principle to tell us of the 5 men, we want to choose 3, and of the 7 women, we want to choose 0. We need to know what's the total number of ways you could have just chose 3 people so that the outcome was not all 3 being men, but what's just the total number of ways, so something less specific. So there are 12 people on the jury, so we'll see 12 as our total amount, and we're looking for the ways to pick 3 of them. So this denominator represents all the possible ways you could pick 3 people for the interviews. The numerator tells me how I would specifically get only men for those 3 people. And that fraction is me using my calculation to make the probability. So so that will tell me the probability that we have 3 men on the jury, on the interviews, I'm sorry. So we can make the calculation here. C5C3 would be our n factorial over, so that's 5 factorial over 5 minus 3 factorial times 3 factorial, which is 5 times 4 times 3 factorial over 5 minus 3 is 2, so that'd be 2 times 1 times 3 factorial. So the 3 factorials can cancel, my 2 can cancel with part of the 4, and we end up with 10 over 1, 5 times 2 over 1. So there are 10 being represented in that area of the fraction. Now we'll make the same calculation for the choosing none of the 7 women. So 7C0, that is 7 factorial over 7 minus 0 factorial times 0 factorial. 7 factorial is 7, 6, 5, 4, 3, 2, 1, all being multiplied. And in the denominator, 7 minus 0 is 7. So we also have 7, 6, 5, 4, 3, 2, 1 in the denominator. 0 factorial is defined to be equal to 1. So that's just multiplying by another 1. So we end up with a fraction where everything cancels, meaning it's equal to the whole number 1. There's only one way to choose none of the 7 women, and that is to choose none of them. And that's why we got the value 1 there. Last combination, so that we can simplify this fraction and talk about the probability, is 12 members on the jury choosing 3. So that's going to be 12 factorial over 12 minus 3, which is 9 factorial, times that 3 factorial. So we get 12 times 11 times 10 times 9 factorial. The 9 factorial will cancel with the 9 factorial in the denominator, and we'll still have a 3 times 2 times 1. I can use the 3 times 2 times 1, that is 6, and cancel that with the part of the 12, and those 9 factorials cancel. So we've got 2 times 11 times 10, which is 220. So we have 10 over 220, which, if I'm looking to simplify the fraction, would become 1 over 22. And as a decimal, that probability would be equal roughly to 0.045. So calculating our probability using fundamental counting principle to talk about the total number of ways to choose 3 men and no women, then using the fraction to talk about our probability overall. All right, that was the last example. The last thing I'm going to show you here is just a summary of counting rules, and this is also found in your book on page 172. We have the fundamental counting principle, which came up in the earlier video, not this video, but we did use it in that last example. Permutations, both types, and the understanding of what a factorial is, and then combinations. Hopefully this video has been informative. If you have questions about the material, please feel free to reach out to me via email. Thank you.